Hello everybody, this is Mr. Brown, and today I'm going to talk to you about energy bar graphs, or energy flow diagrams, or if you need yet another nickname, LOL diagrams, based on the shape of the diagram that we're going to ask you to draw. Um, and that diagram is useful for accounting for the energy in a system before and after some event takes place. And to write for ourselves an energy conservation equation, which can be used to quantitatively analyze the energy in a system. For now, we're not doing the quantitative piece. We're just focusing in on how to tell this story of energy conservation. And as we get more information about how to quantify energy, we can start to add that as a next step to our energy conservation equation, right? For now, our goal is to be able to write that equation and to account for energy and to represent this diagrammatically. So let's take a look at how we would do that. First thing I want to look at is this scenario over here, right? We've got a roller coaster scenario, and that roller coaster is basically functions as a small car that's pressed up against a spring. Presumably a large spring. When that spring decompresses, it sends the car flying around this loop, right? So the first step when we approach a problem with this diagram in mind is to define for ourselves our system. Our system is the object or collection of objects whose energy we want to investigate or analyze. So for me, let's just include everything that we can see here as part of our system. The spring, the cart, the track, and we're also going to include the earth. Anytime we want to consider a system to have gravitational energy or for it to be storing energy in Earth's gravitational field, well, the earth is important to consider. So I'm going to include that as well. I'm also going to make this a perfect scenario where there's no friction, just to make our first analysis as simple as possible. But what we're going to do is go to this first bar graph, go to the center area here, and we're going to write in what is our system, right? And for me, again, I'm including everything, right? And I'm going to go through, I'm going to ask myself a list of questions to help me decide if there's energy that I should include in my system and in what storage account should it be. Right, we've got these three energy storage accounts that show up a lot. There are others, but these are some of the major ones that we'll analyze. We've got the kinetic energy storage account for objects that are in this. We put energy there where there's things that are moving. There's the gravitational energy account, and we put energy there when energy is being stored in Earth's gravitational field. And that's when objects are raised above the surface of the Earth. And elastic energy storage account. That's when things are compressed or stretched. So we're simply going to ask ourselves three questions to begin with. Is anything in my system moving to begin with? No, we have an object that has zero velocity. So I'm going to go ahead and say there's no energy there. Is there anything elevated above the surface of the Earth? No, because we're right on the surface there. And is there anything stretched or compressed? Absolutely, my spring is, right? So I know that there's at least energy in that account. I can represent that graphically later, but for now just a placeholder mentally that there's energy there. I'm going to look at position B. I'm going to ask the same questions. Is anything moving? Yes. So there's energy there. Is there anything above the surface of the Earth? Yes. There's energy stored in the gravitational field. And then, is there anything stretched or compressed? And at this point, no. The spring has done its thing. It's no longer stretched or compressed. No energy there. Last question is the thermal energy account. Is there any reason to believe that because of this event that took place that something would have increased its temperature, would have gained some thermal energy? And if there's no friction, I can't see of a reason why things would have gotten hotter, so I'm going to put an X through that. So we have energy in the elastic energy account at some point, and then in the end it's in the kinetic and gravitational energy storage accounts. One important step to take at this point is to think about our system. Is our system an isolated system or not? By isolated system, what I mean is this system has no energy that's going to come into or out of that system boundary. There's no other objects that this system is interacting with, right? this is it. The spring interacts with the cart, the earth, the track maybe, right? But those objects don't interact with anything else. So the energy will stay inside of our system the whole time. So what we're going to say then is that if the energy is constant in my system, the initial energy is equal to the final energy. What that means is that the energy in this first bar graph has to equal the amount of energy that shows up in the second bar graph, right? So I'm going to just go through it and make that claim. Simply, elastic energy has to equal the amount of energy that's showing up in the kinetic and gravitational energy accounts in the end, right? So visually, I could represent that this way. Say there's 4 blocks of energy. I'm just picking an arbitrary number because I have no other quantitative information about this setup. There's 4 blocks of energy, then in the end, there's got to be 4 blocks of energy. Let's just say there's 2 and 2. Could there be 1 and 3, 3 and 1, 2.5 and 1.5? Absolutely, but for now, I don't have any reason to go with one or the other, so I'm just going to make that claim. Okay, so that'd be one way to do this, but in these LOL diagrams, you have the flexibility to define your system however you choose. Define your system in the way that best serves the questions that you need answered. And some of that will come with experience. As you start to practice these, you start to see strategic advantages to defining your system one way or the other. But I just want to show you a couple examples of how you could analyze this scenario with different definitions of system, or what happens if there's friction involved here. Okay, how we deal with that. Okay, so let's go through a couple of these examples. Let's say there's friction here, right? I'm going to define my system exactly the same. I'm going to write my system right there in the middle, and I'm going to go through and ask the same questions as I did before. In the beginning, position A, is anything moving? No. Is anything above the ground? No. Is anything stretched or compressed? Yes. In the end, is anything moving? Yep. Gravitational energy still? Yep. Elastic energy, is anything stretched or compressed? No. But if there's friction, right, now we have reason to believe that there would be an increase in the temperature of my system. Thermal energy is something that we need to consider now, because as these objects rub together, just like your hands when you rub them together get a little bit warmer, so too will the thermal energy increase in this system. So now we've got some questions to answer. How do I show energy conservation? Well, my equation, I think it's pretty clear. We just say that the elastic energy we had before has to equal the final energy, which now is the sum of all of these energy accounts, right? But I have a decision to make. I want to be consistent with how I analyzed this before. If I said that there's 4 blocks to begin with, in the end there's got to be 4 blocks. Before I said that there were 2 blocks here and 2 blocks here, but something's got to give, because I can only have 4 blocks and I've got 3 accounts to go around, right? How do I do this? To be consistent with what I did before, I said before that this thing had 2 blocks of gravitational energy. If it gets to the same height in this scenario, even though there's friction, I'm going to go ahead and say that the gravitational energy account is still going to have 2, which means that 1 block of energy or 2 blocks of energy have to be divided between the kinetic energy and thermal energy account. Right, so this would be one way to analyze this. Might the actual ratios be a little bit different? Sure, but I don't have any quantitative data to tell me one way or the other. So for now, I'm just going to make these arbitrary claims about where the energy is. What's most important is that we can make this mathematical claim about what's going on with the energy, right? That it's being conserved, and it shows up in the necessary energy accounts. Let's take a look at a different approach here. What if I define my system and I leave an object out? Right? In this case, my system is no longer isolated. The spring is outside of my system boundary, but it's interacting with my system, which means that that opens up the possibility that energy comes into my system or out of my system. So how do I deal with that with this LOL diagram? Let's see. So I'm going to define my system as it is, the cart and the earth. The track is also in there, I suppose, based on what I set up here. I could change that, I suppose. But this is my system, which means when I ask myself those questions, is anything moving? Is anything above the ground? Is anything stretched or compressed? I'm talking about these objects, right? Not any objects that are outside of my system. So what I'm going to say is there anything in my system moving? No. Anything above the ground? No. Is there anything stretched or compressed? No, because the cart and the earth are not compressed. The spring is, and it's out of my system. So I'm not going to include that in my bar graph. In the end, ask the same questions, right? Is anything moving? Yes. Anything above the ground? Yes. The rest of these questions, no. So this is weird though, because now this says that I have 0 energy to begin with, and now I all of a sudden have 4. How do I reconcile that? My bar graph doesn't seem to show energy conservation. Well, what we do in this case is we show energy coming into my system like this. I have 4 blocks. If I had 0 and in the end I have 4, that means that 4 blocks had to have come in. We call this process work. Anytime there's a change in the energy of my system, that means that energy was transferred in or out. We call that transfer work. And in particular, when energy comes in, we call that positive work. Okay? Positive work is energy that comes into our system. So since our system is not isolated, the total energy is not constant. There is a change. We call that change work. And that means that the energy initially plus or minus any work has to equal the final energy. So in this case, we had 0 energy. We had positive work because energy came into our system, and that leaves us with kinetic and gravitational energy in the end. Okay, let's look at the flip side of that. What if we have, look at it from the spring's perspective, leaving the cart and the track and the earth out of it? Well, for that system, we ask ourselves those questions. Is there anything moving? No. Anything above the ground? No. Anything stretched or compressed? Absolutely. In the end, is there anything moving? No, because our spring is not moving. It's not above the ground, and it's not stretched or compressed. So that system has 0 energy. Well, again, that doesn't look like energy conservation, so I have to tell the story that some energy left my system. And I do that this way, by drawing those 4 blocks with an arrow going out of my system. In this case, we call this negative work because energy is leaving our system. So when we write our energy conservation equation, we're going to say energy initial minus work equals our final energy of 0. Okay, so I'm going to ask you guys to try this. I've got 4 different scenarios here with space for you to define your system a couple different ways and to consider or not consider friction. So give those a shot. Ask your teacher for questions about these problems, and we'll see you next time.